Hello everyone and welcome to a new episode of All Things IDA. In a previous video I did a high-level overview of the Decompiler SDK, and this video I think the easiest topic to cover is how to use the C3 visitor pattern in order to extract information from the decompilation output. This is gonna be easy to approach, especially if you've watched the previous video. So with that, let's get started. Before we get started, just like to mention that I did set up a test project that's going to be released on the GitHub repo. I set it up to work with QScripts so I can quickly do some prototyping. So you'll see me having Visual Studio and writing native code in one side and IDA in the other side. So I'm gonna start IDA, and now I should be ready to activate my plugin. Here is the QuickScripts C3 visitor, and now we're ready to experiment. So last time we didn't really dig deep into the code, but let's do that real quick with the essentials. So I have here my main function, and to decompile, like we mentioned last time, we have to start with a function pointer using getFunc. Make sure we have a function pointer, and then we have to issue a decompile call to get the cfunc. Now that we have a cfunc, let's do the first and simplest thing. Given a decompiled function pointer or a cfunc pointer, we can use the get pseudo-code method to get a vector of strvec, which is simple line vector. Once we got this, we will get as a simple line, we will have the line, color prefix and so on, but this line is colored line, so we simply call tag remove. So I'm getting the pseudocode and then simply removing the colors and displaying it. Let's enable this piece of code here in my main function and run it. So here, just build, and once it finishes, I should see the pseudocode output here. So this is the same output minus the colors. If I get rid of that line and just simply assign it to line.line and run it again, we'll see some weird characters, and these weird characters are the colors. This is what IDAView renders nicely in colors and so on. So let's remove this, build again, and continue with much more interesting example. So decompiling just like that and getting the pseudocode is not necessarily very interesting. So what we're gonna do in this video is start to learn how to extract important information from that C3. So in the next example, I'm gonna be talking about the tree visitor pattern, or the C3 visitor, which is all we need here in this code. And the purpose of this code is to extract integer literals. So for example, here the number 2, whatever other integer literals. If you remember from last time when we were using the HRDev helper to show the C3 or the AST, we can see those numbers. So for example, if I click here, it focuses on those, and we can see here part of the call expression, some of its arguments are numbers. For example, here we have num2, we have the second number. So these are numbers, integer literals, and they are nodes in that C3. They are expression nodes. If we quickly go back to the Decompiler SDK and look for COT_num. So COT_num is one of those C3 node types, which comes from CItem, and C expression inherits from that. So if we are to go and find all those COT_num expression nodes, we'd have to start with the function body, which is the C3 root, and we'll have to explore all the linked nodes by hand. So if it's a block, we'll have to go for every linked statement. For every statement, depending on its kind, we'll have to explore. So for example, as we iterate through the function statements and we find an if statement, which is the CIT if, for example, like here, then we know that the if will have its condition in the expression field. It will have a true body and a false body, which are C blocks. So we'll have to go and also explore those blocks recursively. So really it's a matter of tree exploration. Instead of us repeating the same algorithm each time and so on, the HexRays SDK gives us a C3 visitor class. This is a generic class that helps us do a C3 reversal. All we have to do is simply subclass that visitor. When we create an instance, we'll have to specify some flags. Do we want just quick exploration? Do not maintain parent information. So in our visitor callback, every node will have a callback or a virtual method that we implemented will be invoked. And if we specify one of those flags, that will influence which fields will be called and what information is captured during the visitation. So that's the constructor here. We simply constructed give it flags. We have the apply to, which starts the C3 visitation. So that's what we need to start after we have subclassed that class. And then we have to implement either or both visit instructions on visit expressions. So this virtual method will be called each time the C3 visitor, as it systematically goes through the tree. For every instruction, our visit instruction method will be called, and for every expression, which means the expression OP is COT underscore, and here for all the items in the C3 that have the type CIT underscore. So we simply have to override one of the methods that we require. For our example, we are looking for integer literals. This is the simplest thing ever. We have to simply override visit expression, check the expressions is typed to be COT num, and we're good to go. And that's exactly what we have in the first example here. So here I have a function called find integer literals, taking a decompiled function. I have subclass the C3 visitor and specified fast. So I don't care about parent information, and overrode the visit expression, which will give me an expression node for every expression. So here we're capturing expressions, not statement level nodes. And then if the node type is COT num, so here the op types, remember we had a bunch of them, we were just talking about them. So I care about the number. If it's a number, then in the expression itself, I have a helper method called numVal that gives me the value of the number, the integer literal. So if we follow it, first, let's go back to COT num just to show you something. So it says if it's COT num expression, you should check the N field. We can do that as well. So let's see, EN, and just to show you. So the EN is a C number. It's inside the expression. Because its type is COT num, we're supposed to access the N field, which is a C number, which eventually will have the value. Alternatively, for this case as well, there's an expression level helper method called numVal. So numVal behind the scenes will access the N field and the value function. So that's it. After we have subclassed the visitor, put our condition in the visit expression, we can now start the visitation. So we declare an instance of my subclass and call the apply to and give it a starting expression where to start the enumeration from or the visitation from. We don't have to visit just from the body. We can even invoke another visitation from inside our callback. If we found something, maybe then from that node, let's say we found a certain node and we want to see if this is the node we want, and we can't tell that unless maybe we explore its children, we can, if a certain condition applies, we can still call visit from the expression itself as a starting point. So that is also possible. So in this simple example, let me now enable that piece of code here. So now we're calling find integer literals, and it's going to decompile the currently selected function and display all the integer literals that it found. So I'm going to switch to the output here and just build this project. And now what we see is the addresses where we found those numbers and their values. So for example here the 112, this is the 112 here. And if we try to just squeeze in here IDAView, so let's say for example 31 here, this 31, it found it here. So sometimes if it comes up with numbers that are not directly visible in the disassemblies, then that's another story. But remember, every expression or C item, so expression inherits from C item, if it has a related disassembly address that contributed to that AST node, then the EA will be valid instead of being bad address. So as simple as that, with that visitor, with our criteria, what we want. If we found this, we can access the proper field, we extract the value. Now, of course, this might not be enough as a condition, like what's the point of finding integers? We'll see slowly as we progress, we can have complex conditions to extract better information. Okay, now let's progress to another example that captures all function calls. So we want the nodes that have type COT_call, and there are many of them here in this example. So there's so many calls, and we can use the C3 to retrieve those calls. And in particular, I'm interested in direct calls that are calling an address as opposed, let's say, calling a local variable that's a function pointer and so on. This is simply because I put that condition to only capture the things that have a related address in the database. So how do we find all the calls? Same story. We need a visitor and we need to start our visitation from somewhere. Of course, makes sense if we have no starting point to start from the function body. So first I subclass the C3 visitor and then the same stuff here, and simply put my visit expression since the calls are expressions, and my condition is gonna be that node is of type call. For example, this is a call, so COT call, and what is being called is in the expression field X. So here if we follow it as well, the COT call, it tells us you should be accessing the field X in the expression, and those dot 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 means the optional arguments which we'll access through the A member which designates the arguments. So here all I'm doing is simply checking if it's a call, and what is being called is an object that has an address. If this is the case, then all I'm doing is displaying the called address value. So here what I'm going to do is simply message the expressions as address. This is going to be the caller, and then I'm getting the name of the callee, and I'm also displaying the address. So let's enable this piece here, switch to the output window and build this one. So here now what we should have is every expression is address. That means all the callers. So here is the address of the caller, which is at 401349. It's calling printf, which we can see at this address. Then it found another node and another node, and so on. So if we switch here, it basically went over every node and found those nodes. Now you might be wondering, but am I confined to just simply displaying the information? Can I get that information outside my visitor class? Yes, of course. For example, if we wanted to capture those, we can say EA_vec, for example, EAs, and simply have a member variable here to capture the same. EAs, for example, and we can simply assign the callers as EA to it. And here all we have to do is simply push them back, and here we just pass the EAs. And if we didn't want to output this information here, we could have done that. So this is really just a matter of programming. What I'm showing you was the pattern of how we can formulate our condition. So hopefully you realize how useful it is to visualize the C tree using, for example, HRDevHelper. By visualizing it, you get to craft your conditions visually. So if I'm interested in how to find a certain condition, like for example variable and not a function call, I can capture it at the if and go to its condition node. It's gonna be somewhere here, and this is like the logical and, that's the node, and we should have one left child. So let's go down to the variable. This is the variable, and then the next condition is the logical not of a function call, and so on. So if we can visualize the C tree, it's a matter of simply putting all the conditions in the right order and accessing the proper fields of either the expression or the instruction if we were capturing instruction visitations. One more example. Let's go for find all string compare calls this time. So here we want to find the arguments of string compare. So what we have here, calling string compare, some variable, and the string literal. And this is not the only instance. So if I find all of them, I have lots of comparison like this: compare, 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 compare. Can we find calls to string compare and captured what is being compared with? Yes. As well, it's a matter of inspecting this and getting the conditions we need. So if we look at it, we have call X is calling strcmp, so the COT call arrow X, this should give us COT object, and we can get the callee. And then we have two arguments. We don't care about argument 0, we care about argument 1, which is of type some object that has an address, which we can probe to check if it's a string literal. So this is our condition that we can visually identify. How can we express it programmatically? Same story. Start with subclassing a visitor, call your subclass something relevant, build it. Now here in the constructor, just for performance issues, I resolved by name string compare. So here I define string compare to be the name, and I simply captured its address because it's better to check numeric values as opposed to string values. So here in the constructor, one time only I resolve it and save it. Then in my visit expression callback, all I do is just check first if it's a call. So we did this. That's not enough, of course. Then we want to check if what we're calling is the string compare. This is what we want. So let it run. So let's go back here, and now this won't capture the arguments yet, but will simply identify a function that we care about. It will capture the expression exactly, the node, and from that node we can extract information. So here we found all the string comparisons. Now in the next one, I'm gonna show you how we can capture the argument. Okay, now in this function, we're gonna augment the previous example and capture the arguments to string compare. So it's gonna be the same, except that we're gonna extract more information. So we still want to check if it's string compare call. We still care about expressions because this is a call and it should be part of an expression. And so if it's not a call, let's skip it. And now this is the most important part here, which we're gonna check if we're calling string compare as usual, and also we're gonna check the A field. A will be as described in the expression, it says the argument list, which is related as well as it says to a COT call. So we get that same expression that we visited. So the same node, we got the call. Call has arrow X pointing to COT object, and it's calling string compare. So that's what we did. And then arguments, these are argument 0, this is argument 1. And here we're checking if argument sizes, if it's not 2, something is wrong. This is not the right string compare. It shouldn't have more than 2 arguments. It should have exactly 2 arguments. So by doing this, we finished our sanity checks. We found string compare. But now, did we really find the string compare we're looking for? Are we comparing something? We don't care what's the first argument, but comparing with some object that has an address. So this is the second condition. So here I'm capturing the second argument by accessing expression, the COT call, arrow A, and A is an args list. So real quick, let's drill down into it. So it's an args list. Args list is a vector of carg. Carg inherits from expression. So every argument is indeed an expression, could be another function call with its own arguments, and so on. So that's basically the carg. So we're accessing in the vector argument 2. I just simply grabbed it here, and here is the actual condition for the if. It's the argument 2 of type COT object. So are we comparing with some pointer to something in the database, as I said, as opposed to another local variable or something synthetic. So here we can see that call, indeed, its second argument is referring to some address in the database, which is pointing to that string. So this second condition here is what allows us to double check that this is the right argument. And now it's a matter of simply calling getString literal contents to capture the literal string from that database here. So that's what we want. And so this one, let's run it and see the output. It should validate everything and only give us string compares. We didn't care about argument 0, so we only care about argument 1. And here, this is the output coming from here. It says, okay, so I found the string compare here. We didn't really check for whatever is the first argument, and that's what we're comparing with. So hopefully now you're getting the big picture and seeing that it's really nothing complicated. We simply look at the tree, and from the tree we can tune our conditions. Now you noticed every time I wanted to find something, I had to write a full subclass and do the whole thing, and then at the end call the apply to, for example, or whatever helper function we introduce. So this can be tedious. What about simplifying the whole syntax and let us focus on what we're looking for? So if you really want to think about it, to just find something, the thing that really matters in this whole thing is just this piece of code. But we are writing lots of glue code around it, especially that we're subclassing and so on and so on. So this is a bit useless. We can leverage function objects and lambdas in C++ to make this simple. So here, not gonna go much into the details, just quickly walk you through that helper method. So here I introduced a helper method called findExpression, and I simply specified a std function here to allow the user to pass a lambda, and that lambda returns an int the same way as our visit. So the same signature as this one here, which we're gonna be wrapping and exposing as a lambda. So here's then the visitor simply onside the visit expression. All I do is call the function object here, which can be passed as a lambda. And like this, now if I want to find something, the logic should be way simpler. So now if I want to find integer literals, it's as simple as that. It's one function call, find expression. We give it the decompiled function object, and we write the lambda. And in the lambda, I want to only display a message if the expression type is a number. Simple as that. So if we want to compare side by side, for example, this one, the simplified version, and the regular SDK version real quick. So look at that. What we see here, we have the simplified version really focusing on the condition versus here all those lines just to do the same. So of course this is much better. So same story if I look at all the simplified implementations. So for example, simplified finding string compare with the arguments, it boils down to a single function call, find expression. So here the nice thing about using lambdas now is we can capture local variables, so we don't have to pass them to any constructor and so on. So here instead of capturing nothing as before, if I wanted to put the result in some local variable, I could add it to the capture list, and the condition to find calls and dump the arguments remains the same. It's gonna be as well check the argument size. So I condensed all of this to like smaller if condition and so on. And then we capture the first argument and we do the extraction. Can we simplify this code even more? Perhaps. Maybe we come up with some kind of DSL, for example, that lets us write a simple query language, for example, to find those trees, which such things exist, but out of scope for this video. Now you might be wondering, can I do the same in IDAPython? The answer as well is yes. We're gonna look at both things as well, the simplified version and the non-simplified version real quick. So if we start as well, we have to initialize the plugin, we have to go get func, same way like the C++, we have to call decompile, and then to get the pseudocode lines, cfunc that gets pseudocode line, tag remove, and so on. To find integer literals, same story, we have to subclass the C3 and the constructor pass the flags, implement or override visit expression, and same story, Python syntax. Then call the apply to on the function body, nothing changes, same syntax. Here as well, I took the opportunity to also wrap the visitor pattern as well in a lambda. So I also implemented find expression here. In find expression as well, we pass the decompiled function object, the callback or the lambda, and the flags. Same thing, we have the visitor wrapper, which we call the lambda. Then what happens if I want to find an integer literal, I simply define my lambda. This is now, didn't want to put it as a lambda, you can put it, for example, here I put it as a lambda, where you simply find expression, which will print the integer literal. And so simply call find expression, no subclassing, no nothing, and you have all you need. And last thing is I'd like to mention another nice tool set from Dennis as well. So Dennis did HR Dev Helper and also HexRaysToolbox. Now you may explore this project. This project as well uses the same wrapper to provide something like find expression. So you only focus on the lambda that you want to capture the expressions with. So here in this project, some examples. Let's say you want to find any expression that compares anything to 0. So we don't care what's this, but we need to find a node of type COT equal. We want second argument to be an integer literal of value 0. So here, this is how the subtree will look like in the AST. You should find the node of type COT equal. We don't care about X, which is the left-hand side, and Y is the right-hand side of that operator. The right-hand side we care about, it should be of type COT num, and the num value of the expression should be 0. Here, a simple example, we want just to find direct function calls. So we are looking for the callee to be of type COT object. So we want first the parent node to be COT call. Parent nodes is arrow X, takes us to the callee, and we want it to be of kind COT object. So our expression lambda is very, very simple. Find expression. We want the expression should be of type call, and what is being called is COT object. That means it's a direct address. And same story here, a list member mem copy where the destination is on the stack. So we need the COT call, and what we're calling is mem copy, and we are checking arg1 is of type COT var. So as well, that's the lambda. It should be evident. And it goes on for more complicated expressions. As well, you can refer to that project to use some visual aids to help you form the queries visually. So I encourage you as well to visit that project. Okay, so that's it for this video. We learned how to use the C3 visitor to extract nodes of interest, and we also learned how to approach such problem by relying on something visual like HRDevHelper to find the nodes and the attributes and encode what we see in a condition. All right, thank you, and I'll see you next time.